Okay, let's make sure we're doing the right things with microphones. It's the point at which Ronald Reagan would say, "Let's bomb Russia." I'm very glad to be here, and I'm beginning to believe that I actually am. I'm extremely grateful to the conference organisers for giving me a piece of paper with my name on it and a T-shirt telling me where I am, because I may need them later. And yes, I'm just off the plane. If you can read very small writing, the clock in the corner of my screen says Wednesday 23:58, which is what time on Tuesday I actually think it is. And so the plan is basically get it over with before I know what's hit me. Let's see if that just about works. Okay. So I'm going to try to avoid doing anything technical whilst nonetheless live hacking. That's going to be tricky, actually. Didn't really think this through on the plane. Mostly, I want to sort of think about the kinds of arguments that we try not to get into on the internet. Or otherwise can't avoid. See, I'm a second-generation functional programmer. My father, in the late 1960s, added this peculiar feature called pattern matching to a funny language known as Lisp, and started writing quite kind of recognizably modern functional programs with no types whatsoever in the late 1960s. The first serious example was a symbolic differentiation written as a pattern matching program, which of course it is. And so you can see, that's how I came to learn lambda calculus and differential calculus at the same time and far too early an age. And it sort of made basically a mess of my entire life. So you can see that joining the side of the ultra typed people was nothing other than a kind of act of Oedipal rage. But what I want to spend the next hour doing is trying to convince you that it's more than that. So let's see what we can do, because really in fundamental ways, the kinds of things that people say about types, when they're attacking them, or even more worryingly, when we're defending them, do not connect with the ways in which types affect my life in the 21st century. We're having the wrong fight. We're having the old fight. And I want to have a look at a few other things, sort of ideas that have come with us from the 70s and 80s that are still affecting the way we fail to think about typed programming. So it's confession time. As you can see, I'm going to start in Haskell, and this is the beginning of an actual Haskell program. And I'm just going to try to warm up by remembering how to write programs. So, yes, what have we? This is the parser monad I can remember how to implement because of that lovely rhyme. I think it was Fritz Ruhr. A parser for things is a function from strings to lists of pairs of things and strings. So if you can remember that, you're winning. Let's implement its monad instance. So this is just to warm up. Right, we get an input, and we're going to succeed without consuming any of the input, and giving back the x we first thought of. Otherwise, we'll have some kind of parser for a's and some sort of continuation. And we get a parser, which takes an s, and then everything else happens in the list monad, At least it does when I write it. And we apply the first. Note I'm always on for gratuitous use of shadowing to make sure I don't use the wrong S. So something like that. Do we believe that? Well, it type checks, which it didn't a moment ago. And it's gone back to giving me the split screen in the wrong way. Let me just do some Emacs intimidation. We go narrow, we say load. Then we go wide. Right, ooh, I shouldn't give too much away. Right, so what's going on? So I wrote this program. I could, of course, if I'd remembered that this is just the state monad transformer applied to the list monad, have written rather less. But the other thing that I've done is I stuck a thing here, deriving monoid. Now, what does that do for us? I mean, it says parsers ought to be a monoid. We want parsers to be a monoid, right? We want them to have a notion of failure and a notion of prioritized choice. And I'm saying, well, you know, just get that from the types. So, what are the types saying? Are they saying no? They're saying, no, they're not. They're saying, here is your monoid. Is it the right monoid? Well, what monoid behavior will we get? We'll get pointwise lifting over strings, and then we'll get concatenation of the lists of successes. So that is the right monoid. Good. Because we think of lists not just as being some kind of data structure made out of const cells and pointer chains and stuff like that, but we think of lists in this context also, especially when you start writing this sort of do here, as some sort of prioritized choice effect. And the monoid structure for prioritized choice is what gets bundled up with the type of lists. So here's a message. I don't run the mathematically structured programming group in Strathclyde for nothing, you know. These types we write down, they're not just names for data representations in memory. They're tags that queue in mathematical structures that we exploit. So let's do it. So correspondingly, now when I want to sort of weaponize that by making P an instance of alternative, then I just say, oh, just give me the monoid you gave me earlier. And that works just fine. At this point, I could digress into a rant about how if I put maybe here instead of list, I would not get my intended behavior, but I will not digress into that rant. You can look it up in about 10 different places on the internet over the last 10 years. Let me move on. Let me also note that you don't see an applicative instance that corresponds to this monad, yet this alternative instance compiles just fine. That is because I'm not using the same version of Haskell as you. Okay. Let's see if we can remember how to define a parser which eats a character, but only if it likes it. Yes. Giving the game away far too early. Yes, this is one we have to do by hand. What do? We say case S of CS with PC goes to, what do we say? That, I think. Yes? Does that ring a bell? Anything else we say? Nothing. Does that type check? No, what have I done wrong? Give us a hand. Yes, that's one of them. It's great to have so many marvelous helpers in the audience. I'm going to need you. Okay, and now you can tell what's going to happen here, what's going to happen later. I want to write a parser which produces a maybe int given a single digit input, or we should get just the number, and given a dot we should get nothing, and we should be willing to absorb any amount of space up front. So many eat is space. It's a good way to start. And then I told you I wasn't using the same version of Haskell as you. Yes. So what do we need to do? We say just, well, we're going to have to sort of eat an is digit, and then we're going to have to do something to that. Let me try to remember what we do to that. Oh, yes, that's what we do. We cons it onto a funny-looking empty list. Right, and then that gives us a string, which we can then read. Right, that's one option, and the other option is to say nothing, but we have to have the side effect of eating something which is equal to dot. And that's our last option. Is that good? That's Haskell, at least when I write Haskell. You know, I mean, you can read it, you just don't know why it works. I'm happy with that way around. Yes, sorry, these are, of course, idiom brackets. So what's happening is applicative structured things like parsers are being put in argument positions, and pure things are being put in function positions. And the right sort of thing is happening. Let's just show that I tell you no lies. Let's parse with many, well, at least. No, I'm not going to promise to tell you no lies, don't be silly. But let's see what happens if we do that. Yes, we should get lots of different possible parsers, but at least one of them is sensible. Is anyone worrying that this is all a recording? Or am I being sufficiently chaotic to convince you it's the genuine article? Good. Okay, so we've got that. That's some stuff. So we got the alternative structure for free just by grabbing, well, just for the price of the monoid. And you know, that just came from building the thing that goes with the types. So yeah, that's nice. That's one way in which types are not just a punishment for doing wrong things. They are active in writing programs for us so we don't have to. Okay, I think it's next slide time. Right, let's go nuts. I'm kind of fond of these things. So I call this the functor kit. So you can use these to build node structures that you then take recursive fixed points of, if you like. They build polynomial container structures. So let's see what we have. So X always stands for element, or possibly substructure. So we've got the identity functor that just packs up an element. We've got the constant functor, which doesn't pack up any elements. Instead, it packs up some value of A, no matter what the official element type might be. And then we have closure under pairing and choice and composition. So we can build stuff from that. And almost certainly that happens on the next slide. I want to point out there are lots and lots of properties these things have. So in particular, the identity functor is applicative because it just wraps up ordinary values. So the pure just wraps the application is just ordinary application. Then applicative structure, so the ability to sort of send in a value. Am I okay just assuming that people know what applicatives are, by the way? Shout if you're not. I kind of get casual about that. So if we've got a pair, if we're making a pair of applicatives, we can just do a pair of pures and a pair of applications. And if we're doing if we're composing applicatives, so it's nice, applicatives compose, monads don't, then we just lift the inner applicatives operations to the outer applicative. And idiom brackets are a nice way of doing that. What else do we have? We have that the constant functor is applicative in a rather sneaky way if the label-y type is monoidal. Because, so here, remember, when we're using a constant functor, the actual element type it's applied to never shows up. We're not actually talking about functions and their arguments at all. We're just talking about things which live in this monoid. So that's a rather handy one. There are also, yes, that's a good clue to stop here. So so we have got a bunch of data structure building tools and a bunch of mathematical closure properties for them. And then the object of the exercise is to spend less time writing programs. So yes. So here's a type. Notice I'm very carefully making use of the fact that a type synonym does not have to be @kind star. I'm making a synonym for a type operator, and it's the operator that's built from using pairing twice to glom together three elements from the identity functor. Let me just, apologize for one of my favorite perversities is defining infix operators with 3 arguments. I can't stop. I'm addicted to it. But then using them as infix operators at higher type or higher kind. Terrible habit. So if you want to write, these things, the only annoying thing is that to make a triple, it's going to be something like IA paired with IB, that sort of thing. There's a lot of clutter. So I can do that, it's fine. But so what it's nice to be able to do is to say that if we have a pattern, we can just make a pattern synonym. So this is the main reason I use pattern synonyms, and I'm really glad they've been added to GHC. when you use these kind of these functor components to build up data structures, you get lots of generic programs for free because you've built them out of components that have ludicrous closure properties, but your bespoke programs look awful because you see everywhere all of the artifacts of the encoding. So the trick is to define a bunch of pattern synonyms that make the encoded type look just like the type you would have defined anyway. And then you can have the best of both worlds. So let's see. So here's, oh, no, I didn't want to do that. I can see. Oh, that's a bridge too far. Yeah, I was waiting to see whether I would notice that. So was I. And right, so let's sort of see the kinds of things we can do. So yes, I can immediately write down a type of zones, and a zone, because I'm heading in the Sudoku direction, is a triple of triples. And then what sort of stuff can we do? Let's define a zone as with a Z of characters. So zone, that's going to be, we've got to stick a composition on the outside, but then it's a triple of, let's have A, B, C, and then let's do that. Something like that. I'm missing some quote marks, aren't I? Thank goodness for syntax highlighting. And a parenthesis. Is that a zone? Good, that's a zone. Okay, I can even print out a zone. And if I do C compose sequence A, compose unC, and apply that to that zone, I get the transposed zone. Why is that? Because all of the functors in the functor kit are closed under traversability, and identity and product are closed under being applicative, and sequence A pulls any applicative out through any traversable. So in this case, the inner triple is the applicative, and the outer triple is the traversable, and pulling one out through the other happens to do transposition. But, you know, all I wrote down was sequence A. Okay, plus a bit of newtype plumbing that I'm about to get rid of. Do you remember? Who's seen the old Tarzan movies starring Johnny Weissmuller? Yeah, the thing about Johnny Weissmuller was that he was an Olympic swim champion, not an actor. Yeah, fortunately for him, his scenes did not require a great deal of acting, quite a lot of swimming. He adapted to a newfound requirement to swing. But the other thing that he relied on, every plot of such a movie relied on the fact that Tarzan was friends with all the animals in the jungle. And when the plot demanded it, an animal who was a friend of Tarzan would perform some complicated task that would save the day. You know, typically an elephant would do something clever with a trunk or I don't know. The point is this. How did Johnny Weissmuller communicate to the animals which complicated task they should perform? He would always just use the single word, Angwa, regardless of what the task was. And then the animal would do whatever it had been trained to do. sequence A is kind of Haskell for Angwa. Okay, let's have a bit more of that, because we like it, only, you know, let's build ourselves some modern conveniences. There is a newtype library somewhere. I thought I'd just cook it up again, and I thought I'd try doing it with type families instead of functional dependencies for a laugh. This ought to be for free. Anytime you declare a new type, there ought to be something which sort of registers that you've introduced a new type, which is a synonym for some old type. So that's the idea here. You register a new type with the class new type, and you have an associated type family that tells you what the old one was, and then you can do various nice things. So in particular, you give a pack and an unpack. Of course, nothing stops you using this for things which aren't new types, but, you know, bad form and all that. And then you can do some kind of wacky stuff like this, where if you've got an operation that actually works on the old types, you can make it work on the new types by unpacking in the nick of time, doing the operation, then packing up again before anybody notices. So, for example, we could say newly sequence A zone, and then we'll get a hilarious type error. If we say newly sequence A zone and I would like a zone back, then something goes wrong. What have I done? Oh, because it was a zone of characters. Sorry. Then that works nicely. And it's kind of fair enough, because if we didn't tell it what type we actually wanted, then it wouldn't be able to figure out which particular traverse to do. And so what we're paying for by putting the type in is not writing the program. So people who are always terribly keen to insist on retaining type inference should pay attention to the other possibilities which exist. You know, that you might deliberately write types in order not to write code. You know, program inference trumps type inference, says I. Here's another slightly more rococo gadget with the correct order of arguments for its proper infix style of usage. What do we do? Because obviously everybody likes a third order function on a Thursday morning. So what we start with some higher order function, and this time the higher order function actually trades, crucially, in the new types. But we want to use it on the old types. That's the situation. That's to say, there's some new type structure that we want to introduce temporarily in order to get a job done. Sorry. So, we have this completely spurious extra argument whose type is old B to B. That's the type of pack. And we completely ignore this argument. Its only purpose is to tell the type checker, and actually these days, any day now, there will be a release of GHC which just allows you to give a type explicitly as an argument to a function. Has this happened? If it hasn't happened yet, it's about to. Yeah, so, because we've got this sort of, I'll come back to this later. Have you ever noticed that whenever you want to tell GHC a type in the middle of a program, like how you are instantiating some polymorphic function, you can't. Even if you know what the type is that you want, it's like there's a little Simon inside the machine saying, no, 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 I have to guess. And but I'll tell you, Simon, I'll tell you. Yeah, so I'm glad he's finally letting us tell him the answer sometimes. He's not doing it all with constraint solving. So this is a cheap trick from the old days of just somehow telling the thing the answer. What can you do with Allah? But it's designed in particular for use with traverse and for use in infix mode with a nice grave accent over the final A. And yes, so for example, if we traverse a la I, let's say +1 of 0 to 5, then, so traverse using the identity applicative is otherwise known as map. Meanwhile, I can traverse a la the identity, a la the constant applicative, and then I have to say, a la the adding up monoid, what you get when you add 1 to all of these things, and we get 21, which is the sum of the numbers from 1 to 6. It's sort of, look, I'm giving you a bit of a clue what the applicative structure that's going on inside the operation I want to do across this data structure. You sort it out. So traverse a la I is otherwise known as fmap default. Traverse a la K is otherwise known as fold map default. And then fold map a la sum or fold map a la product are all of these things. Lots of very useful operations which all have individual names in the Haskell library are sort of straightforward instances of this thing. So if you really, really want to start a massive war, then propose to enforce the Fairbairn threshold and delete from the library all operations which can be coded up using traverse a la in under 30 characters, and see how long your teeth last. See how long my teeth last. Okay, okay, I was heading in the direction of Sudoku. I'm about halfway through. That's roughly where I want to be. I managed to get just enough free Wi-Fi out of Emirates to rip off this genuine evil Sudoku problem from websudoku.com. And then, of course, I had to spend the next 20 minutes solving it because I'm a bit rusty. I don't want to solve Sudoku just now. I do at least want to parse the board. So let's figure out how to do that. Well, so what we want is a parser for a board. But, not quite sure how to get that. I'll settle for what I can get. I know how to make a board full of parsers. Did we call it p-cell earlier? I think we did. I'll find out. It'll tell me what I've done wrong when I load the file. Let's see. Good. It's heard of p-cell, but it has noticed the type error because so pure p-cell would make p-cell is a p of cell, and then pure of this would, for example, give us a board of P of cell, but we want a P of board of cell. Any suggestions? I think I just heard it. Sequence A. So, and let's do that. Let's see, bit of a mess, but still we can see what have we got. Nothing, 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 2, 3, nothing, blah de blah, compared with nothing, 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 2, 3, nothing, and so on. Yes, and then we decide that because Sudoku is full of lots of symmetry, we want to say let me just grab the actual board, and then I can say newly sequence A, B lives in board of cell, and now we should have the transposed board that starts nothing, 1, nothing, 5, and so on. Same program, modulo a small amount of type wrapping. It's kind of clear that there are parts of the program which are not being directly written by me. And that's where I'm trying to get to. So we've reached the middle, where I will stop fooling about and give the sermon that if I could turn down the seat comfort level at this point. Sorry, too much Protestant childhood. Right. So what is Milner's coincidence? It's an astonishing piece of engineering which took a great deal of very carefully thought out technology, and it has had unintended and profoundly appalling consequences. Let's examine it. We are familiar with the distinction between terms and types, but this is why I wish I could remember what I'd written on these slides. Milner's coincidence allows us to line up the distinction terms versus types with the distinction between the things we write and the things we infer. That was the kind of key thing about the type system of standard ML. You write the terms, the types are inferred. And you've got principal type inference for core ML, and that just became a cultural, wonderful thing, despite the fact that it pretty quickly stopped happening. I mean, we do write types. I mean, sometimes we write types just because we are members of the Scout movement. But sometimes we write types because we forget things. Sometimes we have to write types to resolve ambiguity. Sometimes we're willing to, so type class resolution perhaps. Sometimes we write types because polymorphic recursion is just too much fun. There's clearly a limit to how clever a type system will let you be. Or essentially, if you're not going to write types, your type system has to be stupid enough that a computer can do it. And some people don't want to have a type system which is that stupid, because they don't want to be restricted to being that stupid themselves. Okay. But we also now have the situation that there are things which are not types that the compiler infers for us. So think about all of that heavy-duty type class dictionary construction that you have just not seen, but yet, received the benefit from, right? That's that's inference happening for stuff that's not types. So I'm not trying to say, writing more things for the sake of writing things is, just virtuous and we should all be, good people. All I'm trying to say is that these distinctions do not, in real life, line up. They are both useful distinctions. They're just not in the same place. Here's another one, which you may suspect is rather similar to the second one. Things which are explicit versus things which are invisible. Now, there's a funny cultural assumption that goes on there. Until fairly recently, these two did actually line up rather well. Why? Because how could something be explicit except by you writing it? However, these days, punch cards have given way to teletypes, and it is possible to interact with a piece of computer technology on, a shorter feedback loop. And indeed, to get some things explicit in your code which have not been written by you. We'll see more of that later. Another key distinction that lines up with all of these is whether stuff is around at runtime or whether it's erased by the compiler. So typically, the terms that we have written are retained at runtime, and then somehow types are inferred by the compiler, but then thrown away. You can see how people get frustrated with this. That not only they don't actually contribute to the runtime code, these dratted types. They just get made up for the purpose of telling you off and then thrown away afterwards. I mean, who wouldn't moan about that? This is such a bad deal, right? So if you think about how we, let's start just comparing this with the top one. Right, so we now have things which live at the type level that are really term-like stuff. I mean, the she preprocessor exactly hid a lot of the trickery that people were doing to say, well, since we would like to have these data-like things at the type level, and we've got to make them out of the stuff that's at the type level already, let's just get on and do the encoding. And then, so basically what happened was that I turned up at a Haskell implementers workshop in 2009. The talk's on the video, I'm not lying. And I said, I have chosen the name for this preprocessor so that I can make truly appalling jokes non-stop until you implement all the features in this preprocessor. And they took me seriously. And they implemented data kinds and pattern synonyms. We've just got to work on them for idiom brackets and a few other bits and pieces. Right. Meanwhile, Simon is doing his nut, trying to improve the quality of runtime representation of types. So the whole of data.typable machinery is exactly about saying types aren't around at runtime, so we have to give you something else that is around at runtime, that lives in the term language that stands for the types, and then try and arrange for equality testing on those runtime simulacra equality testing and pattern matching, somehow to deliver some useful impact on what the type system knows about what your program is doing. That's to say, what's missing is honest-to-goodness types at runtime. You should, you know, yeah. So because you can't have them, you have to make something that's a bit like them. So what I'm trying to say is that this presumption that runtime versus erasable lines up with terms versus types is now causing genuine pain and adding a great deal of complexity to the way we do things. Unnecessary complexity. So yes, I just did that. I claim that terms versus types and runtime versus erasable are entirely orthogonal. What I ought to do is just remove some spaces. There's a, yes. And I guess I also just wanted to say something about writing versus runtime erasability. Exactly, you've seen me writing types which are going to get erased in order to get inferred runtime terms. So, I mean, this is such a win. Right, you know, I'm perfectly happy to write simple high-level specifications that don't make it to runtime as long as the execution of my design is inferred for me and executed. I mean, that is such a win. Okay, and the other thing that we have that lines up with all of these is that we have non-dependent abstraction for these things and explicit quantification over these things. And again, that's just sheer prejudice. Serves no earthly purpose. Now, I'm not saying that I want to realign these things differently. In particular, although I am in favor of types being permitted at runtime, I do not say that types should always be at runtime. I would like to have a for all that quantifies over types at compile time only. That should say that are erasable, and a different quantifier which quantifies over runtime types. And one of those quantifiers will have a strong parametricity property that I really don't want to lose, and the other one won't. So that's the thing that Richard Eisenberg is not implementing because he's trying to graduate or something daft like that. Good luck to him. No, he should graduate. I thoroughly recommend that he graduates. Right. Oh, yes. And I guess this is the cue to get on with it. Yes. Well, I kind of already said that a large part of this problem comes from the fact, I mean, why we have this idea that types are there just to tell us off is that, you know, we have this idea that we search for code in the domain of ASCII garbage. And we try and construct a lump of ASCII garbage that might be a program without using tools that do terribly much to distinguish one bit of ASCII garbage from another. And then we send it to the compiler and we get a torrent of abuse. I mean, yeah. And if that's our workflow, we've got problems. But that doesn't have to be our workflow. So let's look at what happens in a different programming language. Yes, this is a hopefully quick example. I can see time's marching on. If you were at my ICFP 2014 talk, you will have seen me fail to deliver this message clearly because I was trying to deliver several other messages at the same time. So what I want to show you is a computer working hard. Don't we all like watching computers work? I'll work a bit, but the computer will work a lot. Okay, so what I want to do, first of all, just as to build up a simple example, is to define a notion of evidence. Right? This is the great thing. Once you start using types as an input, you get paid back if you make them more precise. So I'm going to start by talking about using not Booleans, but some actual evidence to explain ordering relationships on natural numbers. So, okay, I'm making use of type information to do case splitting for me. And then I think, so this is a typical dependently typed programming move. We think, what evidence would convince us that 0 is less than or equal to y if they're both natural numbers? Well, I should have thought that was fairly obvious. So I will accept the simplest evidence I can think of, namely an element of the unit type. So the blue things are types. The red things are value constructors. So I'm saying the evidence that 0 is less than or equal to y consists of just some trivial value. Otherwise, if the left-hand number is a successor, I'm going to have to think about it. In particular, I'm going to have to look at the number on the right. Okay? And I'm going to define that if the thing on the left is a successor and the thing on the right is 0, there is no evidence whatsoever. So the empty type will serve as the type of proofs that a big number is smaller than 0. And then if I'm trying to check whether the successor of x is less than or equal to successor of y, I will be happy if you just show me that x is less than or equal to y. Okay, so that's one way to define the relation on natural numbers less than or equal, by saying what type would constitute valid evidence for that proposition. And now I want to solve the problem of how to show that if you have two natural numbers, x and y, then either x is less than or equal to y, or y is less than or equal to x. I'm terribly sorry. When I write Agda programs, I'm much more likely to take co-products of types than to actually, add numbers together or whatever it is people used to do with computers. So, so I just use the arithmetic symbols for type operations. Okay, so I think Agda knows how to write that program. I like to do this sometimes. When I do this in class, I always have a camera on my fingers. All I said was, you figure it out, and you're allowed to do case analysis. And it said, oh, go on then. So, there's... Right. Better hurry up. Okay. Next slide. All I'm doing is I'm gluing a bottom and top element to the natural numbers that I can use as bounds for things like binary search trees. And I'm extending the definition of the ordering relation for bounded things. So in particular, the bottom bound is below everything, the top one is above everything. And things in the middle are one's less than or equal to the other if the original definition says so. Otherwise, that's false. And then I can define what it is to be an interval between a lower and upper bound. To be in an interval, you have to give me an actual value, which is above the lower bound and below the upper bound. So that's a useful type. And then I introduce the type of ordered, balanced 2-3 trees. What fun. So a leaf is a 2-3 tree of height 0 between a lower and an upper bound, and to construct one, you must show that the lower bound is below the upper bound. A 2-3 tree of successor height, of a non-zero height, is either a 2-node or a 3-node. The number refers to the number of subtrees they have. So a 2-node has some value x, which is the key stored in the node, and is used as the upper bound for the left subtree and the lower bound for the right subtree. And you can see the subtrees are one shorter than the whole tree. And then what's a 3-node? It's the same sort of thing, except that we have 2 keys stored in the node. So the left subtree is below the left key, the middle subtree is in between the 2 keys, and the right subtree is above the right key. Everybody got the picture? And the whole idea is that having the possibility to make 2 nodes and 3 nodes of the same height allows you to do amortized rebalancing of the tree. But it's also important to note that in any kind of binary tree structure, which this is, there is one leaf in between every 2 keys. And that's why putting ordering information at the leaves is enough to ensure that successive elements in the structure are actually definitely in order. So we're maintaining the order invariance, we're maintaining the balance invariance. Okay, goodness me, I've got like a handful of minutes. Can I possibly write insert? Let's see. One thing that helps you write insert is to realize that insert will only go wrong by producing a tree that's slightly too big. And if it's too big, it'll be the stuff that makes a 2-node of the next size up. Okay, I'm not going to write the whole function, but I'll give you the general idea. What happens? We've got to do 3 nodes. And I've got to change the names of everything in sight because Agda uses terrible names. So this is going to be a T, LX, TXY, TYU. Okay, so what do? We compare X with Y, so the value we're trying to insert, with the left key. And we see what comes back. And then I case analysis on what comes back, and I get 2 possibilities. And the fun case is going to be the too big case, or the, well, no, it doesn't matter which one. So here we learned that X was Y. Now we know, in this case we know which subtree. We know we're going into the left subtree, because X is below the left key. Okay? So I say with insert something into the left subtree. Whoops. I really have lost the plot. Sorry, folks. TLY, and this should be YZ, and then it actually makes sense. Alpha conversion may be free. I haven't, yes, let me just fix that. But it's not, names may be arbitrary, but it's nice to get them right. Okay, we know we need to insert something into the left subtree, which is TLY. Okay, what shall we insert into the left subtree? Well, there's only one thing we can insert into the left subtree. There's only one thing that we know lives in the same interval as the left subtree does. Our comparison just established that X is in sufficiently tight bounds to be a candidate for insertion into the left subtree, and it's the only thing that is. So absolutely no harm getting the type checker to figure that out for us. And then let's see what comes back. Well, in the case, so the nasty case is the too big case, and that's the one we clearly have to look at. We either have a V and a TLV. If the subtree that comes back from the insertion is the same size as before, then we can just reassemble the thing without causing any problem. So that the fun part is this part. Need a comma. Right. So that's all the stuff. Right. So what I now say is subtle. I say, dear Agda, can you think of any trees like that? And it says, well, you can have the tree you started with, or you can have this nicely rebalanced tree that's too big, but which contains the element you were hoping to insert, because it contains this thing which had X inserted. So I say, I'll have the second one, please. And there we go. And yeah, all of the, so what I have to do in writing this program is choose the analysis strategy, synthesizing the appropriately rebalanced trees is a matter of choosing from a menu either the tree I started with or the tree I want. Every single case. So, okay, I should stop with the confession that it took me about 15 years to come up with that type for it. I was doing other things as well, I hasten to add. But, so that's my question, really, is to think how we can make better use of the way types act as a problem statement. Okay, so what you see here is, I write down a really nice type for a function, and all of, I get paid back time and time again for having made such a good design choice in the first place. Right, I'm really just making the few choices that are left that weren't already fixed in advance by the type, and that's great. The code, I'm not quite sure it yet is a readable record of problem-solving interaction, but here's the crucial point, that for most of the time, you discover when you do one of these refinement, charge, I've got my type, I'm refining it to my program, oh, my design's wrong. And at that point, it is like the opposite of the Wizard of Oz moment, right? You have to switch off your type checker, your file goes back into black and white, you're in Kansas again. And you have to think, I'm back in the space of ASCII garbage looking for the next type that I'm gonna, go wild for. And the question that we really face is how to do better than that. Okay, I'm happy to stop there on that disturbing note.